In the previous module, we considered a world consisting of a system and bath. We studied how the number of configurations of the world varied with the amount of energy transferred from the system to the bath. In this module, we use the Boltzmann factor to produce a list of formulas used to calculate average properties of such a system. We found that the number of configurations in which we can find the world, given parenthetically that the system's energy is held at squiggly e, was the number of ways to find the system at energy squiggly e, multiplied against two factors that together give the number of ways to find the bath. The factor in yellow is the number of ways to find the bath in the reference situation in which no energy is allocated to the system. And the green factor is a correction for the fact that some energy has been transferred to the system. There is a large number of configurations in which we can find the world. The number W cis plus n of squiggly e counts up a subset of those configurations, specifically the collection of configurations of the world in which the system has precisely squiggly e energy. If the time spent in each configuration were equal, then the system energy squiggly e that corresponded to the greatest number of configurations W cis plus n of squiggly e would be the system energy most often observed. As we have said, the fundamental postulate of statistical mechanics states that an isolated world explores all accessible microstates equally. In this slide deck, we are transferring energy between system and bath, but not between the world consisting of system and bath and anything outside the world. Thus, each of the configurations of the world is equally accessed. The system energy most typically observed is the one corresponding to greatest W cis plus n. In this sense, one can say that the number of ways is maximized. When we take the natural logarithm on both sides, we turn products into sums. The Greek letter sigmas are called entropies. They are the natural logs of the ways W. Maximizing the number of ways W cis plus n corresponds to maximizing its natural log sigma cis plus n. In other words, the system energy squiggly e most typically observed is the one for which the world's entropy is maximized. Flip the green and blue stuff and then place both on top of a common denominator tau. Factor out a negative sign so that the squiggly e looks positive inside the square brackets. The stuff inside the square brackets is called the free energy of the system at energy squiggly e. Notice that the entropy of the world and the free energy of the system are distinguished by a negative sign, a denominator of tau, and a constant, meaning the entropy of the bath at the reference condition in which all of the world's energy U0 is allocated to the bath. These differences are somewhat superficial. The free energy of the system is the entropy of the world in disguise. As a consequence of the negative sign that distinguishes the free energy from the entropy, maximizing entropy corresponds to minimizing free energy. The system energy squiggly e most typically observed is the one that minimizes the free energy of the system. What fraction of time does the world spend in configurations with a given system energy squiggly e? Because accessible configurations are explored for equal times, the probability of finding the world in a configuration with a particular system energy squiggly e is the ratio of the number of ways the world can be configured with that system energy versus the total number of ways the world can be configured with any system energy compatible with conservation of overall energy of the world. We already have the expression for W cis plus n from above, and now we can conveniently cancel out the common constant factor of W bath U0. The denominator is given the special name of partition function and denoted by the letter z. If the partition function can be written down for a particular system, it can facilitate the calculation of the averages of properties of the system when the system is connected to a large bath. For example, consider the energy of the system averaged as the world explores its accessible configurations. The viewer can verify that the bottom line can be obtained by taking a derivative of the natural log of the partition function with respect to temperature, which may be more convenient than direct calculation. In these video modules, we have described the fundamental postulate of statistical mechanics, briefly introduced notation for working with configurations of objects with many parts, and considered how energy is likely to be apportioned among parts of an isolated world in order to be able to calculate properties of a system connected to a bath.